This is a review of net ionic equations and solubility rules. So net ionic equations, we often will abbreviate NIE. So if I have that written next to an equation, that will indicate that I'm writing the net ionic equation for that. The idea with net ionic equation is that, first of all, these only apply to things that occur in aqueous solution. So if you have a solid and, a gas reacting, does not apply because we're only talking about ions that are in aqueous solution. The idea is that we are going to omit spectator ions. So we want to think about what ions are actually involved in a reaction. Pretty much what you're doing is you're starting with a double replacement reaction in aqueous solution, and you're getting rid of the things. Instead of thinking of them as entities together, you're going to be more realistic in identifying that sodium chloride in aqueous solution is not actually a bunch of NAs and Cls close to each other. It's sodium ions and chloride ions completely separated from each other and in fact surrounded by water molecules. So let's talk about the solubility rules a little bit. There are innumerable ways of writing the solubility rules. This is just one. When we say solubility rules here, of course, we're not making up these rules. This is just from experimentation and repeated observation. So there are some substances that are always soluble. Sodium ion, if it has sodium as the cation, it is soluble. Potassium ion, if it has the ammonium ion involved, that's why you got to know your polyatomics and recognize them, and the nitrate ion. So if the cation is any of those three, or if the anion is the nitrate ion, you know for sure that it is soluble. Sometimes people will remember that with SNAP, so sodium, nitrate, ammonium, and potassium. Okay, so those are always soluble. So if you see that you have a compound listed, this one's an obvious one, sodium chloride, as soon as you know that it's sodium, you're good. It definitely is going to be aqueous. If you have some kind of thing like lead nitrate, lead ions, things that contain lead ions are often insoluble, but because it has the nitrate, that means that must be soluble, so you would write aqueous next to that. Or if you saw aqueous, it would hopefully make sense. Okay, so those are the always solubles. We also have some often insolubles. I'm sorry, I wrote that wrong. These are actually often soluble. So not always soluble, but often. So the halogens. So anything over there, if I have, sodium chloride, right, is aqueous for two reasons. It has sodium ion, which is always soluble. It has chloride ion, which is often soluble. So if I have calcium chloride, I don't really have to worry about the calcium and thinking whether that is soluble or not. I'm going to focus on the chloride. Often soluble, but not always. Then we have the often insolubles. So those would be lead, if it contains lead, if it contains silver, if it contains barium. So if I have lead 2 chloride, yes, it has chloride, which is often soluble, but if you see something with lead, pretty good chance it's going to be insoluble, unless, of course, it's lead 2 nitrate, because the nitrate makes it always soluble. Okay, so if I have made that thoroughly confusing for you, some of that just does come with practice. There are solubility charts, there are solubility rules, there are a million ways you can represent that. As far as the AP exam goes, if you know that first list of always solubles, that'll be enough for you to determine what's going on. Some of that just comes with seeing lots of things, or you can look things up. Okay, let's try an example of writing a net ionic equation. So let's do a simple one first here. So if I have sodium chloride, I know that is going to be an aqueous solution because it is soluble. It contains the sodium ion, done. Silver nitrate, that is also going to be aqueous because, not because of the silver, but because of the nitrate. Then we write that as a double replacement reaction. So that means I'm going to get sodium nitrate. Gives us two reasons to be soluble in that one, right? The sodium ion and the nitrate ion. And then silver chloride. Chloride is usually soluble, but silver is in my list. And if silver chloride was not insoluble, then you would have no reaction. You would just mix some things together that do not form a precipitate, and you have a clear solution and a clear solution, and you mix them together and you get another clear solution with 4 types of ions in it rather than 2. However, silver chloride is insoluble, and so it would fall to the bottom. It would precipitate to the bottom. It is like a white powder, if I remember correctly. Okay, this one was pretty easy to write, the overall reaction, because all of these made +1 ions or -1 ions, and so I didn't really have to worry about my subscripts too much, right? 1 sodium and 1 chlorine go together, 1 silver and 1 nitrate entity goes together because nitrate is -1. I'm not looking at the charge of a nitrogen ion or nitride ion or an oxygen ion, nitrate. So I will sometimes write these this way. If I'm trying to think through it, I'll just think, okay, what are my ions? And now how would they go together? Yep, a 1-to-1 ratio for everybody. Okay, in order to write this now as, so the way I'm going to write it now, you pretty much are never going to want to leave this as the final form. This is just and you will be able to shortcut past this quickly, but that's what you actually have in your beaker, right? You've got sodium ions and chloride ions, and you've got silver ions, and you've got nitrate ions. Once you pour your 2 solutions together, they're all just hanging out in there, surrounded by water molecules. After the reaction, I have sodium nitrate, which is also soluble. So that means I've got silver ions and nitrate ions separated from each other, not ionically bonded, because that's a soluble compound. So it means to be soluble. But my silver chloride actually is bonded to one another. I've got clumps of billions of sodium ions and billions of chloride ions that are held together by those strong ionic bonds, making crystals, powder that falls to the bottom. This form of the equation is just as accurate as the top equation that I wrote. Just takes a lot longer to write. What we're going to do now, though, is get rid of the spectator ions. So the spectator ions are ones that didn't really do anything. They're in the stands. They're not playing the game. They're just there, but they're not experiencing any change. So sodium was aqueous to begin with, aqueous to end with. Nitrate was aqueous to begin with, aqueous to end with. So you don't need to write them because it's kind of pointless. Didn't really do anything. So what you actually have are chloride ions and silver ions in aqueous solution, making silver chloride. I almost always write these this way with the cation first and the anion next because I think it looks nicer. Oops. I need a reaction arrow there in order to make silver chloride. Now, as you might have noticed, the shortcut of this is just write your overall reaction as we did up here, as if just writing a double replacement reaction. Look to find the insoluble product. So if I write my insoluble product first, after I kind of know that top reaction, what ions would be required in order to make that insoluble compound? I would need silver ions in aqueous solution, and I would need chloride ions in aqueous solution in order to make silver chloride. The fact that there's sodium ions in there and nitrate ions in there is a true fact, but they don't appear in the reaction. Let's try one that's a little bit harder. So in this case, I'm going to have copper 2 chloride. So let's write out the names here first to review also how we know how to write the reaction. So we've got copper 2 chloride, because of course copper is in there in those transition metals that can have more than one possible charge. so you have to specify in the name. And then we have potassium phosphate. We're going to mix those together. So let's write the formula. Copper 2 ion is Cu2 plus. Chloride is Cl minus. Potassium makes a +1 ion. I'm getting those from periodic table, 1 valence electron, which it loses to have to make potassium. Phosphate, got to know your polyatomic ions. That's 1 phosphorus, 4 oxygens covalently bonded to it, but an overall -3 charge. I know the phosphorus and the oxygen are covalently bonded because those are nonmetals, but that whole entity of PO4 of a phosphate ion acts as, obviously an ion, hence the name. Okay, so when I write the formula for copper 2 chloride, I can't just say CuCl. It has to be CuCl2. And if these are going to be in a double replacement reaction, they have to be dissolved in water, otherwise it doesn't make sense. In order to have electrically neutral, the way we would write the formula for potassium phosphate is if I have +1s and -3s, I'm going to need 3 of those +1s in order to balance out 1 phosphate ion. Okay, so that's what I'm mixing together. Let's write it as double replacement. If a reaction occurs, the only possible reaction could be copper with phosphate and potassium with chloride. So copper and phosphate, this one's going to be a little more complicated because we are going to have copper ions and we are going to have phosphate ions, and we have to figure out how to write the formula. I cannot write the formula based on how many there are on the left side of the arrow. I have to write it based on the charges of those ions. So I've got a +2 and a -3. Least common multiple is one way to think about this. Least common multiple between +2 and -3 is 6. So that means I'm going to need 3 of these copper 2 pluses and 2 of these phosphate ions. So that means I'm going to need 3 of those and 2 of those. That is copper 2 phosphate. Has nothing to do with how many of anything are on the left side of the arrow. And then I have potassium chloride, so I'm going to have potassium ions and chloride ions. How are those going to go together? Just a +1. Okay, potassium chloride we know is going to be aqueous because it contains a potassium ion. Copper 2 phosphate, we don't have any rule for it all. But it is insoluble because it says so, if we looked it up. Or the other way to know that copper 2 phosphate is insoluble is because quite often the problem statement will say something along the lines of copper 2 chloride and potassium phosphate are combined, a precipitate of copper 2 phosphate is formed. So if they're telling you a precipitate is formed, you don't even have to look up any solubility rules. They're already telling you. Okay, let's try the shortcut method for this. I know I'm going to make copper 3 phosphate, and I know that it is solid because problem told me that a precipitate forms. What has to go into making a copper 2 phosphate? Well, according to I didn't balance the equation. Let me do that. 1 copper and 3 coppers, that's no good. I'll do it in a different color. When we balance the equation, we've got 1 copper on the left, 3 coppers on the right. So let's put a 3 here. That would give me 6 chlorides when I do that. So that means I need to put a 6 here. That gives me 6 potassiums, which means I'd need to put a 2 here so that 2 of those K3PO4s would be required. Okay, so that gives me 6. Double check everything. If you wrote all your formulas correctly, then this will balance easily. So 3 coppers, 3 coppers. A total of 6 chlorides, right? We've got 3 times 2. Each copper 2 chloride has 2 chlorides, and I have 3 of those. So of means multiply in math. 3 times 2 is 6. Yes, that's what I have on the right because there's a coefficient of 6 in front of potassium chloride. 6 potassiums, yep, that's what I have on the right. And I have 2 of those phosphate entities. And that's what I have on the right also because that's what the parentheses are. Now, let's see what we get. In order to make 1 of those copper 3 phosphates, I would need 3 copper ions and we were told this was copper 2 plus, and I would need 2 of those phosphate ions in aqueous solution somehow in order to pour them together into the same container, and you get your precipitate. In other words, in order to make copper 2 phosphate, I could get my chlorides or my coppers there from copper chloride. I could have gotten my coppers there from copper 2 bromide, probably. You know, something that provides coppers is all we really care about. The chlorides and the potassiums were just a vehicle in order to get the ions that I needed for the reaction. Because I can't have a beaker of just copper ions, right? That if there were no anions to balance those out, that would have an overall positive charge. That is not stable. So whenever we need an ion, we have to get it in the form of an ionic compound, but then it's just going to have some other ion along with it that we don't really care about. It's just in the beaker, doesn't react. It's there to start with, there to end with, aqueous to start with, aqueous to end with. That's why we don't write it in the net ionic equation. AP loves net ionic equations, so get in the habit of recognizing those and writing those. We'll practice it lots and lots all year. Okay, hope this was helpful.